we're now going to get onto the last equation that we're going to be discussing, and that's the trajectory equation. So we've seen that the trajectory of a projectile is naturally described by a parabolic curve. However, it's actually derived in terms of a cosine translation. So there's a lot of trigonometric identities going on in here. However, as a proper formula in quadratic form, this is the actual formula in simplified terms. But we can also write this as y is tan ax minus, well, we have g over 2u squared cos squared a times x squared. So that's it in quadratic form. However, it's always best to leave it in non-quadratic form the way that it is in the red box. So the proof of this is slightly arduous, and it does require some trigonometric identities. So I'm going to go ahead and show you the proof. Here it is. So just filling in some general information, it's going to be at some point xy after some time t. So x and y are the corresponding sx's and sy's. The speeds remain the same, the accelerations remain the same, and the time remains the same. We're just doing everything completely generally. So starting with sx equals uxt this time, we can say that t is x over u cos a. Now putting this into the y equation, which is u sine a t minus 1/2 gt squared, these u's cancel, so we get y is u sine a x over u cos a minus g over 2 times x over u cos a squared. So what we end up with is y is x tan a from our identity before, minus g over 2 times x squared over u squared cos squared a, which fully simplifies down to y equals x tan a minus gx squared over 2u squared cos squared alpha. It is a slightly arduous proof, and it is a very annoying equation. However, it is very useful for tracking the path of a particular projectile, and can also help us to estimate the trajectorial path.